So at this point, we're at about the halfway mark in our class, which means that we are going to enter this new section of content that is kind of like a repeat of what we've done, just applied in a little bit different way. So far for this first half of class, we've been talking about kinematics and kinetics of a particle. So everything that we've looked at so far is just one little dot in space, something that we've zoomed out so far to treat it as just a particle, just a point, when we're analyzing it with our kinetics or with our kinematics, right? So our force, acceleration, work, energy, momentum, all of those, velocity, acceleration, all of those, we're looking at something like it was a particle, right? So for example, we had things like a car, very zoomed out, we were just treating it as a single point, or like a skier on a hill, we were treating them kind of as a single point. And for this next portion of class, that'll be not all of, but most of the rest of the class, we're going to look at this, everything that we've learned so far, look at this kinematics and kinetics from a little bit different perspective, and it's going to be for a rigid body. So instead of looking at something like it's just a point in space and analyzing it, now we're going to look at it as if it's the full body of whatever the thing is, whether it's this parent boot that I've drawn or whatever shape it may be, where it may matter that we actually take into consideration that this thing is a full body. For example, if I take this pen, for example, maybe I'll use a little bit brighter pen that you can see a little bit better. I don't know if that's any better. Do I have something darker? Yeah, that's a medium color. So for example, when we were having things move as a particle, it was acting kind of just like a point in space moving around. But with a body, with a rigid body, we may want to account for things like rotation, where one end of the body is moving while another end is staying still. Or we may want to account for rotation like of a basketball, where it rotates about its own axis, right? So we have that rotation, you can see that little pin clip coming at you. So maybe there's some type of rotation, maybe it's moving through space in some kind of abnormal way that we can't really treat it like a particle. We need to treat it as the particles in this guy are kind of moving differently from each other, so we can't really zoom out to treat it as just one dot in space. We're going to need to account for it having a full entire body. And so that's what we're going to be focusing on with kinematics and kinetics for the next several weeks. And so essentially it's going to feel like a repeat a little bit, right? You're going to see a lot of the same names, a lot of the same concepts. We're going to be talking about kinematics, force, acceleration, work, energy, momentum, all of these same topics again, but applied to a rigid body instead of a particle. And so today we're going to start that. We're going to give this introduction of our planar kinematics, so planar motion of a rigid body. Now, a rigid body just means that the body isn't deformable. If you end up taking strength of materials, there we typically talk about how does a body deform and that sort of thing, but we're not going to really deal with that here in dynamics. We're just going to say everything is a rigid body. It's not deforming at all. It's going to stay perfectly the way it is no matter what forces you apply to it. It's not going to bend or twist or do any deformation like that. Instead, we're just going to assume it's a rigid body, and we're going to see how the body itself moves, starting with our kinematics. So in this video, we'll kind of introduce our kinematics and a few of the different ways we see it before we move into those kinetic concepts. So with our planar kinematics, what we're really looking at here is planar motion. And so what that means is basically we're not really looking at like 3D motion per se, where a pin is like, maybe spinning and coming at you and like going through lots of crazy 3D motion. Instead, it's going to be all within a plane, right? All of the particles of that rigid body are going to move in paths equidistant to a plane. So this is mostly going to be 2D that we're looking at for now. We will look at 3D towards the end of our class, but everything we're looking at for now is pretty much in a in a planar sense of motion, in this kind of 2D sense of motion, that we're talking about for our rigid bodies. And there are really three types of this planar kinematics that we may see. The first one is translation. And this is essentially if our body is, here's our body, it moves either in a rectilinear way, or it moves along a straight line. Now it's over here, or maybe it moves in a curvilinear way. Now he's up there. Right, so rectilinear, if we take our pin again, rectilinear, the pin just moving in a straight line, or it could be moving in a curvilinear motion, going in a circle. Think like, kind of like a Ferris wheel is a good example of a rigid body that would be going through this planar kinematic motion. You can think of the little seats that go around in the Ferris wheel. They don't move up or down. All of their particles stay in line, like they stay in line with each other, even though they're going through this circular motion in space. Right, so they are a body. They are a rigid body. We can also kind of sometimes think of them as a particle, but we can think of like a Ferris wheel as a good example of a line of like your lines of your particles within a body kind of staying in line with each other and going through that motion. That's translation. Okay, so we'll say typically rectilinear or curvilinear, as we've kind of seen in the past. Another one you might see, or I should say will see, we will definitely go over all of these. We're going to talk about each one of these in way more detail. This is just a nice introduction for you. Our next one that we'll see is rotation about a fixed axis. And that one kind of gives it all away right in the name. Right, rotation about a fixed axis. So if I have, here's a rod or something, and it's going to rotate about its center. Right, that would be one example of rotation about a fixed axis. If you are really good at spinning a basketball, you can spin a basketball on your finger. That's rotation about a fixed axis. Taking this pin and just turning it between my fingers here, that would be rotation about a fixed axis. So that's another one that we may see. And the last one that we'll see is called general plane motion. General plane motion. And what this is, it is a combination of the two before it. So a body will be translating and rotating at the same time. Translating and rotating. So that could be something like, maybe we had a translation of a rectilinear motion, but also it's spinning about its center axis and moving like this. Right? There could be rotation about the center axis while moving through curvilinear motion, something like that. So it's going to be a combination of our translation and our rotation is our general plane motion. And each of these are going to get kind of their own videos, their own segments, their own overviews with their own rules of how we treat each of these scenarios. In this one, we'll go ahead and introduce our translation and how we deal with that. So for our translation again, that just means that our body is moving somewhere in planar space, right? Somewhere within a plane. So for example, we likely have some XY plane, and we have some body that's being translated somewhere in that plane. Where we're still in our plane, we're just not necessarily located at the origin. So when we're thinking about our kinematics, our position, velocity, acceleration for our translation, what we're doing is we're going to relate particles that are within that body to our origin, to our coordinate system. So one way that we commonly do that is with our position vectors, right? So if we're going to relate our position to where we are in this moving body, this translating body, I can go from the origin to some arbitrary point A, and from our origin to some arbitrary point B, and those will give me position vectors of RA and RB for the body. And I can relate those two together with our relative vector RB with respect to A. So with this, I can set up some relationships to find the positions of my particles within the body itself, right? If I want to know if one end is, like hypothetically down the line, if one end is moving at a different speed than another, I can go ahead and use A and B as these arbitrary points to see what that body is doing. So here, my position B is of course defined by our relative motion. RB is RA plus RB with respect to A. But when I take a derivative of this, my position of B with respect to A is never changing, right? That vector RB with respect to A is never going to change. The body itself is not changing. That distance between A and B there will never be changing. So taking a derivative, this term is going to go to 0. And what I'll get is that my velocity of B equals my velocity of A. And if I take another derivative, my acceleration of B is going to be my acceleration of A. So what this is really telling us is that anytime we're going through this translation, the whole body velocity is going to be the same throughout the body. The whole body acceleration is going to be the same throughout the body. And the really, really important thing, the reason why I mention this and why we talk about this at all, is because this is going to let us use our Chapter 12 kinematics and pretty much treat a translating body like a particle. So translation of a rigid body can be analyzed using the same kinematic equations, same kinematic, we'll say relationships, same kinematic relationships as particle motion. And since we've already gone over this pretty extensively, how a particle moves, the kinematics of that, we're not going to go through it anymore with our translation here. Just know if we have a body that's moving, we can use those exact same kinematic relationships that we learned way back at the beginning of class to solve translation problems for a body that is either moving rectilinearly or curvilinearly throughout space. So thankfully that takes care of the first of our 3 types. And as we kind of go down the line, our types will get a little bit more complicated and we'll talk about them more in depth in future videos.